The last topic that I want to cover in fluids is viscosity. And we're not going to go over this topic in great detail because it's actually fairly complicated. Um, but it is, if you've noticed that, not all fluids will flow as easily as others. And so you have something very thin like vinegar, which will flow very freely, or water. But if you have something thicker like oil or even something like honey, then they do not flow very quickly at all. And so we want to try and model this behavior of why some things flow more easily than others. And so we can kind of define viscosity as a resistance to flow. So there's some kind of structure to the way that the fluid is made, and it just resists wanting to flow. Either there's some sort of frictional forces, inside the fluid, or we're not really sure. I should say we're not really going to cover it. We're just going to try and model it and come up with a better way of understanding it. So what we're going to think about is that if we have a fluid flowing through some volume right here, then that fluid is going to flow with some average velocity. But really, it's not the same velocity throughout. There's going to be a velocity going into the pipe and a velocity on coming out of the pipe. And the pipe will give a length L. And so this change in velocity is due to the pressure differential. So this could be, say, a high pressure side, and this could be the low pressure side. And the pressure on the low pressure side could be just P. And we're just going to model the high pressure as the P, the pressure on the low, plus some additional amount of pressure, delta P. Okay. So this pressure differential, delta P, we're going to model as with an equation, which we're going to get basically from experiment. So we build a pipe, we take a fluid like vinegar, we pour it through the pipe, we measure the velocities, we measure the different parameters of it, like the length of the pipe, the area of the pipe, and we come up with an equation that says 8 pi eta times the length of the pipe, the average velocity, and the area of the pipe, like so. Where these parameters, this average velocity is just looking at the velocities at either end of the pipe and then just dividing by 2. We'll take the straight average from there. But the eta is the coefficient of viscosity. So this is a thing that is material dependent. It depends on what kind of a material you have, whether it's oil or vinegar or honey or ketchup or motor oil or water, or even a high pressure gas. So that's the thing that you have to really, this is understood experimentally. So with this one, at least right now, what we're imagining is that you go into the lab and you just get all the different materials and you repeat the same experiment, measuring basically the pressure change on both sides, and then you kind of come up with a coefficient, which you can kind of think of like as it's a material dependent coefficient. The other parameters have some kind of experimental meaning as well. And so if you think about it, if I make the length bigger, so if I increase the length, then the change in the pressure gets bigger. So there's a bigger difference between one side of the pipe and the other. So if we're thinking about this viscosity as something that's slowing down the fluid, the longer we make the pipe, the more the fluid is going to have to now maybe have friction with the sides, the walls, and it's going to slow it down. Whereas on the other side, if I open up the area, if I increase the area, then the pressure should decrease because now I'm giving it more space for this fluid to flow through the pipe. And the other one is if I change how fast these are if I increase the average speed, then the change in the pressure should also increase, because what we're kind of doing is we're making a larger difference in the speeds between the left-hand side and the right-hand side, the entrance to the pipe and the exit to the pipe. So we basically, the picture I'm trying to paint is one where we have a pipe and we have this volume of fluid which is moving through the pipe like this. So here's our fluid. Okay, so it's a volume which is moving along. However, this is if there's no viscous property to it. Instead, if we add viscosity, then what happens is we basically slow down the fluid that's on the outer edges, and the ones inside, the interior of it, are going to be moving faster. So if you kind of think about it, is the fluid on the edge of the pipe is going to be clinging to the edge of the pipe, and it's going to have some sort of friction, so it's going to slow down. And then so maybe if I can try and draw it. So if here's the pipe, then I can think of there's some fluid on the edges over here, but then there's some fluid which is now clinging to it's not touching the edge of the pipe, but it's touching the slower fluid. And then you have fluid which is a little bit faster now. And so you get these kind of regions where you have basically fast moving fluid, a little bit slower still, and then the slowest. And so in the end, what you get is this kind of gradient, a change in the speeds of the fluid, and it's basically the slower fluid is trying to cling on to the faster moving fluid and such. Okay, and so if we throw this all together, the volume flow rate, that's delta V over delta T, and then the volume is, or I could calculate as the area times the average velocity, my average velocity now, I said, was A divided by A, the coefficient, viscosity, pi, the length, and then delta P, and all of that times the area. So I throw in my equation for the average velocity into my volume flow rate. You know, if my area is a circle, pi r squared, where r is the radius of the pipe, right here, then Q becomes basically delta P area squared over 8n pi divided by the length. If I throw in that circular area, I have delta P pi squared r to the fourth over 8 nu pi L. One of the pi's canceled, and I'm left with pi radius to the fourth power delta P over 8 times viscosity times the length. And so this is known as Poisseville's equation. So basically, it's kind of it's a experimentally driven equation, but what it tells us is that the rate at which the fluid is moving through the pipe depends on a very unique condition, and that is it's proportional to the radius to the fourth power. So changing the radius of that pipe is going to dramatically change the way that the fluid is going to flow through the pipe. So you can increase the flow just by increasing the size of the pipe a little bit. You can, well, and you can also change the pressure, but the pressure goes linearly with the flow rate. You could shorten the length, and that would increase your flow rate, but a lot of times that's constrained by the problem. Or you could change the fluid. You could change to a fluid which has a lower viscosity, and then the fluid is going to flow much more quickly. So the thing that has the most dramatic effect is changing the size of the area, changing the radius, or in this case we're using a circular area, changing the radius because it goes as a factor of r to the 4th power.